Thank you very much for this very kind introduction. Thank you very much for the invitation to be here. It's really a pleasure. And let's make this interactive. So I'm going to talk a new idea today. I'm going to present something I haven't presented before. And I would very much like to have a discussion about this. My talk is going to be about neuroengineering, more precisely cognitive neuroengineering, and even more specifically, machine learning for cognitive neuroengineering. The main question that really motivates me is, how do we link cognition to neural activity? And obviously with the aim of predicting how we should change neural activity in order to treat certain cognitive disorders. And I believe that we don't really know yet how to do this theoretically, and I hope that my work provides some new insights and maybe some small steps towards solving this problem that is central to cognitive neuroengineering. So, but setting the stage. Our brain is this marvelous system that can do many, many things. But if things go wrong in the brain, this gives rise to various cognitive disorders like stroke, epilepsy, amyotrophic lateral sclerosis, depression, schizophrenia. And a large percentage of the worldwide population is affected by such disorders with cognitive deficits. Now, the way that these disorders are treated nowadays is, of course, sometimes psychotherapy, a lot of drugs, and that's because these drugs, they act on the chemical signaling pathways of the human brain. But we know that the brain does not even use chemical, it also uses electrical signaling. And my vision is really to use neuroengineering to intervene on the electrical signaling pathways of the human brain to treat cognitive deficits. And I think this has one potential huge advantage over drugs. And that is that drugs usually act globally on the whole brain. But if we have some technology available to stimulate the brain with a high spatial-temporal resolution, then it should be much more simple to customize treatments, to personalize treatments for individual patients. And my goal is to develop the machine learning methods that kind of provide the blueprint how to achieve such a personalization. So what do we need for that? Obviously, a brain. We need ways to record neural activity. We need ways to translate neural activity into cognitive states, and then to predict how we should change neural activity, and then we need actuators that control neural activity to achieve the desired cognitive effects. And what we can do with that, I group into three different topics. We can try to replace cognition, in the case of brain-computer interfaces, where we try to provide a new communication channel to locked-in patients. We can attempt to restore cognition, where we only use this technology as an intermediate step, for instance, in stroke rehabilitation, until patients have regained some cognitive skills. Or we can also use it to extend cognition, like these rats here from the